In the next section, we tackle inverse circular functions. Now, recall that a function has an inverse only when it is one-to-one. But the circular functions are not one-to-one. In particular, they are periodic. So there are some horizontal lines that intersect their graphs at infinitely many points. To define inverse circular functions, we restrict each of the circular function's domains such that the circular function is one-to-one on the restricted domain, and the range of the restricted function is the same as the original one, so that the domain of the inverse function is still the same as the range of the original circular function. For instance, consider the sine function, part of whose graph is shown here. Clearly, it is not one-to-one. But if we restrict to the closed interval, negative pi over 2 to pi over 2, then the curve now satisfies the horizontal line test. And the range is preserved. It's the closed interval from negative 1 to 1. So we will define an inverse sine or an inverse function on this restricted function. Recall once more that the graph of the inverse is obtained by interchanging the x and y coordinates of the points on this graph. As a result, we obtain the reflection about the line with equation y equals x. And so the green curve here is the graph of the inverse sine function. And we have the following definition. Okay, the closed interval -1 to 1 here is the range of the original sine function, and it is now the domain of the inverse sine function. For any x in the closed interval -1 to 1, the inverse sine of x, which we denote in this manner, sine with a superscript of -1, is the number y satisfying x equals sine y, and y is in the closed interval negative pi over 2 to pi over 2. In other words, the inverse sine of x is the angle in negative pi over 2 to pi over 2 whose sine is equal to the given value x. All right, let's have an example. Okay, let's evaluate the inverse sine of square root of 3 over 2. Now, if we let y to be equal to the inverse sine of square root of 3 over 2, this means that sine y is equal to square root of 3 over 2, and y belongs to the closed interval negative pi over 2 to pi over 2. Okay, so we're looking for an angle in negative pi over 2 to pi over 2 whose sine is equal to square root of 3 over 2. What is that angle? Well, first it must lie in the first quadrant because the sine value is positive, and since the y coordinate is square root of 3 over 2, then this is the special value pi over 3. Okay. Note that there are actually infinitely many solutions to this equation. For instance, 2 pi over 3 also satisfies this equation. Sine of 2 pi over 3 equals square root of 3 over 2. And we can add integer multiples of 2 pi to these two angles in order to get all the solutions to this equation. But in this interval, negative pi over 2 to pi over 2, we are sure that there is only one solution to this equation. And in this case, it's pi over 3. Next, what about the inverse sine of 0? So we're looking for an angle from negative pi over 2 to pi over 2 whose sine is 0. And when does sine become equal to 0 on this interval? Well, at the angle 0 itself. So the inverse sine of 0 is 0. Next, what about the inverse sine of negative square root of 2 over 2? Okay, we're looking for an angle in negative pi over 2 to pi over 2 whose sine is negative square root of 2 over 2. So because the sine value is negative, it must lie in quadrant 4. And since the value is negative square root of 2 over 2, then this reference angle must be pi over 4. This angle then, which should lie between negative pi over 2 and 0 is negative pi over 4. Note that this angle is coterminal with 7 pi over 4. Okay? And in fact, it's coterminal with infinitely many other angles because we can add integer multiples of 2 pi. But again, this is our chosen range. And so we choose the representative, negative pi over 4, and not 7 pi over 4. Next, what about the inverse sine of negative 1? Okay, which angle from negative pi over 2 to pi over 2 has a sine value that's equal to negative 1? It's negative pi over 2. And I hope, again, it's clear why the answer is not 3 pi over 2. Okay, our answer should come from this range. Lastly, let's have the inverse sine of 2. So we're looking for an angle from negative pi over 2 to pi over 2 whose sine is equal to 2. But when does sine become equal to 2? Think about it well. Actually, it's impossible, no, for the sine to be equal to 2. And this is undefined. Remember, sine values only come from negative 1 to 1. Okay, so this is undefined. And don't forget, the domain of the inverse sine function is just the closed interval, negative 1 to 1. Right? Now, the inverse or the other inverse circular functions are defined similarly. The domain of each of their domains is restricted such that the restricted function is 1 to 1 and has the same range as the corresponding original circular function. In particular, we choose the closed interval 0 to pi for cosine, the open interval negative pi over 2 to pi over 2 for tangent, etc. Note also that the inverse sine, inverse cosine, inverse tangent functions are also denoted arcsine, arccosine, arctangent with capital A's. Right? Let's illustrate these restricted domains for easier reference when we evaluate inverse trigonometric functions. Okay? So the range of the inverse sine and inverse tangent function are subsets of negative pi over 2 to pi over 2. The ranges of the inverse cosine and the inverse cotangent function are subsets of the interval 0 to pi. And note that the ranges of the inverse secant and the inverse cosecant function both represent the first and third quadrants. But note that the representatives for the third quadrant are different. Okay, let's have some examples. Okay, let's evaluate the inverse cosine of square root of 3 over 2. Okay, so what does this mean again? Okay, so first inverse cosine comes from 0 to pi. So we're looking for an angle from 0 to pi whose cosine is square root of 3 over 2. Okay, so since the x-coordinate of the point must be square root of 3 over 2, this angle must be pi over 6. Next, what about the inverse cosine of the inverse cosine or the arc cosine of negative 1/2? Again, we're looking for an angle from 0 to pi whose cosine is negative 1/2. So it must lie in quadrant 2. Okay, so since the x-coordinate is negative 1/2, this angle must be 2 pi over 3. Okay? Next, what about the inverse tangent of square root of 3 over 3? Okay, this is the range of the inverse tangent function. So we're looking for an angle from negative pi over 2 to pi over 2 whose tangent is square root of 3 over 3. So this lies in quadrant 1. Now notice that this is the same as 1 over square root of 3. And we can think of this as the ratio of 1/2 and square root of 3 over 2, meaning the sine value must be 1/2 and the cosine value must be square root of 3 over 2. So the angle must be pi over 6. Next, for the inverse tangent of -1, we're looking for an angle, again from -pi/2 to pi/2, whose tangent is -1. And since the tangent value is negative, it must lie in quadrant 4. And this number means that the sine of the angle and the cosine of the angle are negatives of each other. So the reference angle here must be pi over 4. And so this angle must be -pi over 4. I hope you're following so far. Okay, what's the inverse cotangent of negative square root of 3? Okay, for the inverse cotangent, we have this range. Okay, so we're looking for an angle from 0 to pi whose cotangent is negative square root of 3. Okay, so the ratio of cosine to sine is negative square root of 3. The cosine must be negative while the sine is positive because the angle must lie in quadrant 2. Okay, so now we may think that the cosine must be negative square root of 3 over 2, while the sine must be 1/2. So the cosine is negative square root of 3 over 2, sine is 1/2. So this angle must be 5 pi over 6. Now what about the arc cotangent of 0? So we're looking for an angle from 0 to pi whose cotangent is 0. So cosine over sine must be 0, meaning cosine must be 0. So the angle must be pi over 2. Next, what about the inverse secant of negative square root of 2? Okay, so we're looking for an angle, either in this interval or this interval, where the secant is negative square root of 2. So it must lie in quadrant 3 because the secant must be negative. Okay, secant being equal to negative square root of 2 means that the cosine must be negative square root of 2 over 2, the reciprocal of this number. So since the cosine is negative square root of 2 over 2, again, this reference angle must be pi over 4. So this angle here must be pi plus pi over 4 or 5 pi over 4. Lastly, let's have the inverse cosecant of -2 square root of 3 over 3. Here we're looking for an angle in this range whose cosecant is -2 square root of 3 over 3. So it must lie in the third quadrant also. But note that our representative must lie between -pi and -pi over 2. Okay. Now this ratio is the same as -2 over square root of 3. So the angle must also satisfy, or sorry, the sine of the angle rather must be negative square root of 3 over 2. Okay, so since the sine is negative square root of 3 over 2, this reference angle must be pi over 3. So the angle that we are looking for is -2 pi over 3. Okay, I hope those examples are enough. Next, let's discuss the graphs of these functions. Again, please know the graphs of these functions by heart as we will be using them to evaluate limits. These functions are all continuous on their respective domains, so their limits are computed by substitution, except at the ends or at the tails of their domains. Okay, this is the graph of the inverse sine function as derived earlier. And this is the graph of the inverse cosine function. Again, both of their domains are equal to the closed interval -1 to 1. The range of this is -pi over 2 to pi over 2, while the range of the inverse cosine is from 0 to pi. Now, note that uh, x may only approach 1 from the left in this case and -1 from the right because it's undefined beyond -1 and 1. And say, based on the graph, the limit of the inverse sine of x as x approaches -1 from the right is negative pi over 2. The limit of the inverse cosine of x as x approaches 1 from the left is 0. Okay, and then you can make similar statements for the limit of inverse sine x as x approaches 1 from the right. Sorry, from the left, and the limit of inverse cosine x as x approaches -1 from the right. These are the graphs of the inverse tangent and the inverse cotangent functions. Their domains are both equal to the set of real numbers. Again, they are continuous everywhere. And based on the graph, the limit of the inverse tangent of x as x approaches positive infinity is pi over 2. Meanwhile, the limit of inverse cotangent x as x approaches positive infinity is 0. The limit of inverse tangent of x as x approaches negative infinity is negative pi over 2. And the limit of the inverse cotangent x as x approaches negative infinity is pi. All right. This is the graph of the inverse secant function. What is its limit as x approaches positive infinity? Based on the graph, it's pi over 2. And what is its limit as x approaches negative infinity? Well, it's 3 pi over 2. Finally, this is the graph of the inverse cosecant function. And its limit as x approaches positive infinity is 0. And its limit as x approaches negative infinity is negative pi. Again, please be familiar with the graphs of all the special classes of functions that we have encountered so far. I would suggest preparing a sheet of paper containing the graphs of all of these functions for easy reference.